What are you doing? Are you happy with how rainy it's been? No? Did everybody get stormed on at least a little bit? I did. I got really wet today. You'd think I'd remember to bring an umbrella, but never. I always get drenched. So I'm going to start today with a mea culpa. So do you guys know mea culpa, right? Means my bad, right? So last lecture, I clearly tried to fit in way too much material, and because of that, I think it ended up being more confusing than elucidating, and that was my fault. So I apologize, first of all, for that. And as a result, I'm going to back up a little bit and try and at least clear up some of the confusion. So last time, one of the things that sort of got us bogged down was we had all these equations for doing cost estimation, and how we do it is not that important. We sort of got bogged down in all of the logic behind why we divide by 3 when we have a selection statement. That doesn't matter so much. Obviously, we can do better. Real database systems do actually do better, right? We're trying to learn sort of a model of generally how databases do this thing. I'll provide for you the estimation equations on the exam. So don't worry about memorizing. Make sure that you can use them. But again, they're not the important part. The important part is that we can do this cost estimation. If we have a query plan, we can estimate its cost. So for example, I showed this query, right? Which was basically if we started with a SQL query that looked like this. Select distinct from these two relations R and S, where A equals 10. We would imagine that we would end up with a query plan initially that looked something like this. Assuming R and S had some common natural join attributes. So we could estimate, given all those parameters that we start with, what the cost would be of executing this query. And again, it's not so important how we do it, but we should percolate up the tree all of these costs. So we should start at the leaves and work our way from the bottom up the tree, combining each one of the operators along the way until we get to the root, which in our case was the duplication elimination operator. Once we get there, we've estimated the cost all along the way, all the way up the tree, and then we finally add up that total cost along the way, and that is our estimate for this query. So that's for that particular query plan. We could rewrite that query plan. So generally one of our heuristics that we thought, generally would help us do better was the notion that we could put selections down, and we could push duplication elimination operators down. So let's see what that looks like. So that was the next query plan that we wanted to estimate the cost for. And here, again, the specifics of how we, this is all just plugging in equations. The important part is that the final cost in the end actually is less. So those heuristics actually did improve the plan. So if we were going to, go out and execute that, one of these two query plans, we would obviously choose the one that had the lower cost. Okay. So before I move on to the next thing, does everyone understand how, in principle, we do those cost estimations. They're just flat out a matter of plugging in to each one of the equations that we have for estimating each one of the operators, those values that we have for the number of distinct tuples, the number of distinct attribute values, etc. Okay, so the thing that I think caused the most confusion was this notion, what if we're joining together a whole bunch of relations? You have a whole bunch of tables, and I showed you guys that it's not an option for us to go through and enumerate all possible plans. So I think from 173 you should have seen things like this. That basically, this is a combinatorial issue. So the number of binary trees with n leaves, we can count that. If you don't remember how to do this, it's not that important. The whole point here is just for me to show you that this is computationally infeasible. So if we had 10 joins, like I said last time, there would be on the order of 18 billion different just join orders. And then we have to concern ourselves with, for each one of those given join orders, we also might be able to push down some of the duplicate elimination operations or selection operations. How far down the tree should we push them? Each one of those considerations is going to add more. There's a combinatorial explosion happening here. So one thing that we decided to do straight off the bat was, just for simplicity, for our own sakes, let's only concern ourselves with left join trees. So this is one specific kind of topology where we always join relations together and then join one more relation to the result of that and then join one more relation to the result of that all the way up the tree. So it creates this nice little structure. And the thing that's nice about it is there are only so many, so there's one tree topology, that's fixed. And then there are only so many ways we can rearrange the leaves, right? N factorial. So we could, for example, instead of, initially I showed R, S, T, U, we join them in that order. Now we can rearrange them here. So we join R, S, then U, then T, etc. So we're only going to concern ourselves with that for all the rest of, the course. Don't worry about all the crazy topologies. And then the point that I tried to get across to you was that if we want to do better here, if we want to improve, we can use dynamic programming. If we want to try to find this optimum query plan. So instead of just naively trying all possible permutations, we can try the same trick that we use in 473 of building, partial results along the way and then saving those results so that later we can reuse them. For example, if we know the cost of a query plan that looks like this, then that would be helpful when we want to compute the cost of all of these query plans where we're just joining on one more table. So I wanted to go through this example again, and hopefully this will be more clear. Now I have pictures. Hopefully we'll all feel enlightened after this. So the first thing that we have to do, so every single time we're starting with subsets of a specific size. So we'll start with subsets of size 1, one relation. It turns out we don't even really need to do any work there, right? How many ways are there to join that one relation by itself? If I join R to nothing, I'm not doing any work. The cost is 0, nothing happens. So my dynamic programming table that I've drawn up here, I didn't bother with the subsets of size 1 because they have no cost, and because they're input, they also have no size. when I consider subsets of size 2, there are two different ways, potentially, that I could join, for example, R and S together. Right? I could join R to S, or I could join S to R. In terms of our cost estimates, the cost of those things is the same. So again, there's only one way to do this, and it's not that interesting. The only thing that we need to concern ourselves with is actually plugging into our equation for estimating size the specific numbers for the relations R and S. So we can do that, and we end up getting an estimate for the size of the result of joining those two tables together. And, the plan for joining those together is just R join S, and the cost is also 0. That's going to be the same for every single one of these size 2 subsets. The only thing that will change is the size of that intermediary table. The cost of all the rest of them is, again, 0. So, okay, we have that done. Now things get a little more interesting. So now we're going to consider subsets of size 3. For example, R, S, and T. So the reason these nodes in here are in red is because those are the ones that we've already computed. So we're going to assume, right, all subsets of size 2, we already did that work. It's done. It's over. So that is known, and we're just going to add one more relation to each one of those results. So in this case, we have these R, S, and T relations. We just have to concern ourselves with, which one is the last one that gets joined in. So the size estimate, there are some shortcuts that you can take to do this size estimation a little bit more easily by hand. You can look that up on, how exactly to do that. The cost, though, the cost is related to, so what did it cost for us to join R and S together? Part of that equation is the size of that result. So we can use, right, so we found the best way to join R and S together had a cost of 0, but a size of 5,000. So our cost will also incorporate that size. Yes?
Is cost in terms of just read?
So our cost in this is in terms of size. It's in terms of just purely overall number of tuples.
So there's 0 tuples?
What's that?
So when you do the R cross S, the cost is 0 means that there's no tuples?
No. It's the cost of the number of tuples that we have to read. So we're not concerning ourselves with the fact that when we read in S and when we read in R that there was an output, or sorry, that there was an input, because we read both of those off the disk, right? They're initial input, so we don't count them. Okay, but we have to concern ourselves with all of the different possible ways of doing this, right? So this is just one way of joining R, S, and T. This is another way of joining R, S, and T. We can join R and T and then join S. That, it turns out, the cost is really high for that. We could join S and T and then join R. The cost of that is 2,000. It turns out that that is actually the cheapest. Right? That one has the lowest cost. That is the one that we will save. So each one of these entries, we're going to save the cheapest plan. We're going to save the cheapest cost, and then we're going to keep the size, overall size, around. Right? We're going to remember that. So we can repeat that process for all the subsets of size 3. So now we have the best plan for joining any three of those relations together. Now we have that finished. Let's concern ourselves with joining subsets of size 4. Oh, question? Yes?
So how did you get to the size for str was 10K? Should it be the minimum of RS, RT, and SP?
So you're asking the size here? How I got, for example, this size?
Yeah.
That comes from the equations that we have for doing size estimation of joins. So I would encourage you, for now, let's not worry about that, okay? Feel free to ask me after class or in office hours if you can't remember how to compute that or you can't figure out how to compute that. I don't want that calculation to confuse the rest of how we do this. The main thing that I want you to get right now is the overall flow of the algorithm. Computing each one of these things is just plugging in equations. But each one is built up in terms of this dynamic programming. So I want to make sure that you can understand how we're filling out the table, how we're deciding these query plans. So now we're concerning ourselves with subsets of size 4. And you'll notice I'm saying here, for example, I'm joining R, S, and T. I don't know, I haven't drawn what the best query plan is for that. At this stage, I don't care. I already found the answer. So I'm going to use the best query plan that I found so far, and then find the best way of joining U onto that. And then I'm going to repeat, the same thing. I know what best query plan for joining R, S, and U. What is the cost when I join T onto that? I concern myself with all of these different possibilities, and I will find the overall optimal query plan. So first I can find the cost of joining S, T, and R together, and then finally joining U onto the result of that. That cost is $12,000. Then I can concern myself with joining R and S together, then U, then T. And then finally, the cost of that is $55,000. The cost of this query plan is $11,000. The cost of this last query plan, though, joining R on at the end, the cost is only $3,000. This is the query plan that we will choose. This is our final answer. So as long as you can follow at least the overall query plan, the overall dynamic programming that I just demonstrated, if you can follow that, the rest of it is all just plugging in equations. The rest of it is all just take all those estimation equations that we computed before, that I showed you before, and plug in the numbers. And if you want, I'll post the specific equations for this, if that makes it easier for you to see. Oh, yes?
So if we were doing a join of R, S, and U, since the R, S, T, and U query is cheaper in general, would we do a projection then? Like first join R, S, T, U, and then project away T to get R, S, U? Because that seems like it would be lower cost.
So we can't change the actual query result, right? The person who wrote this query in the end wanted all of these relations joined together. We have to give them that correct result. So we're not allowed to add extra operators in here if it would change what the result is.
Well, I'm saying if we were joining R, S, and U instead, then it seems like the R, S, T, U query is more efficient.
So you're saying it would be better to join R, S, and T?
No, sorry. If we're calculating RS, if we're trying to join RSU together, then it seems like it's cheaper to join RSTU and then project out T, because that's the cost of $3,000 instead of the cost of $5,000.
I'm not sure what you mean by projecting things out. If we're projecting out some relation, like we're actually like doing work and then throwing it away.
Yeah, but it seems like it has a lower cost in general. The cost of doing all of them is somehow more expensive than just doing R as an
We have to, in the end, like join all of them together.
Well, no. What if the query that the user sent in wasn't TUS and R? It was just RS and U.
If it was just RS and U, then we would want to find the best query plan for joining RS and U, which we found.
Which we have it.
Right?
So the question is it worth it to do T in there as well, seeing as that only takes 3,000 and use something else to get rid of the T in there?
I see what I understand now. So you're saying if we wanted, for example, to join all of these things together, could we first, like if we just wanted RS and U joined together, right? Could we join everything together and then like throw away the T part of things because it's cheaper? No. The reason that this is cheaper to do this way is by joining T and U together, we've thrown out a bunch of stuff, right? Only the things that join between T and U stay. Only those tuples are in that result, right? So actually, the efficiency that we're seeing here is because when we join, two specific tables together, more tuples get thrown out. Those tuples getting thrown out would actually, if we then like project it out, if we then got rid of, for example, U, we would be missing tuples. Yes, that was a good question. So it actually would change the result. And you have to guarantee correctness.
On every insert, we have to calculate this again, right?
I'm sorry?
On every insert to a table, we have to recalculate this table.
Yes. So if someone alters the underlying table, we would have to potentially recompute the statistics and recompute the table. We'll actually recompute this thing for every single query that someone gives us. This is not so bad. Computationally, this is pretty fast. Compared to the alternative, which is choosing all, possible doing numbers.
But when we recompute this for every single query, wouldn't we already have the query answer?
So, no. I mean, if someone wrote a different query, right, it's going to involve different tables. I actually will after this. So the next thing I'm going to do is, I think what I'm going to do should make all of this really clear, especially with questions. So before I get to it, though, we have to finish this up. So I really rushed through this last time. So now we have this notion of the physical query plan. So I want to elaborate on this a little bit. So we talked all about the logical query plan, right? What did the logical query plan consist of? What was in our logical query plan? It was like a tree. What was in there? What were the nodes?
It was relational algebra.
Right, it's all consisting of relational algebra operators. If one of those relational algebra operators, for example, was join, we talked about a bunch of different ways to do a join, right? We said that we could do it with a hash, we said that we could do it sorted, we said we could do it one pass, two pass, we said we could use even an index, right? That zigzag join. We have all these different options. The physical query plan is when we choose among those options. We actually decide specifically what algorithm we're going to use. So we're going to replace all the relational algebra operators and substitute the execution algorithms that we talked about a couple weeks ago. And we're going to make decisions about which one of the algorithms that we use based on how much memory is available, right? So we need to know how many buffers we have. We can't do the one-pass algorithm if our memory size is too small, for example. We need to know, are the relations that we're working on indexed? Right? We can't do an index-based join if the underlying relations aren't indexed. That won't work. Are the results sorted? So if someone has gone through if we decided that we were going to use, for example, a sort-based join, all those tuples are coming in from that sort-based join. The output of them will be sorted, right? So they will come into the next operator already sorted. We could take advantage of that. So maybe we want to know that. So if we're smart, we can take advantage of these things. There's also another issue. We need to know whether we're going to pipeline or materialize the results of each one of the operators along the way. So have we discussed pipelining and materialization yet? Those should be mostly foreign words. I kind of hinted at what they were. But the basic idea is this. So we talked about how we would implement all those operators. Along the way, if we get finished with a particular block, right, we've executed our algorithm, we have an output block, we could take that output block and just write it out to disk. Or, if we know that some other algorithm, one of our other operators, needs to do some work on that block, we can actually keep that block in memory and do the next one as well. Right? So that would be pipelining. Pipelining means keep the results in memory and just pass the blocks between all the different operators whenever we can. Materialization, if we don't have enough memory buffers, sometimes we can't do pipelining. So we have to write the results back to the disk. When we do that, it's going to give us two intermediate I/O operations. Because we have to write each one of those blocks out to the disk and then read it back in when we want to operate on it next time. So here's what a physical query plan might look like. So we have, in the leaves, we have essentially how we're going to access each one of the different relations. So a table scan would mean we would just scan that relation in one block at a time. Maybe we could also do an index-based scan, right? If there was an index on that relation, we might be able to access its entries directly through the index. Then, as the tuples from those relations come in, right, as we see each one of the records get pulled in off the disk, we're going to do some algorithm on them. So in this case, we have the two-pass join. That was when we decided what our physical query plan would be. That was what we decided it was, and we require a certain number of buffers, so we're going to add that in. So every single time in the internal nodes, we have to pick what algorithm we're using, and we have to pick how many buffers. So there's one last little weirdness here, and that is this symbol, these little two lines. Does anyone have a guess what that means? That's it again? Yes? So it's actually indicating whether we're pipelining or we're materializing. When we see those two lines, it means we're materializing that. It got too big, we need to write it out to the disk. As opposed to if there are, not those two lines, that means that we're pipelining. So let me show you what that might be. So let's say we have this exact same type of query, except now each one of the relations that we have is out on the disk, and its primary key is A, right? So they're all sorted by our join entry. This is just a hypothetical. So when we scan the tuples of that relation in, we're actually going to get them in sorted order. Let's take advantage of that. If we have, for example, that two-pass sort join, if the tuples are already coming in order, then we don't need to do the first pass. It's already been done for us. Okay, well, that's great. And then we can also, because these are coming in sorted order, we could pipeline those. So when we bring in a block from relation R, when we bring in a block from relation S, and we merge the results of those together, we'll get some other block, some output block. we could read in a block from you and join those together, and then write that whole thing out to the disk. That's the advantage of Python. That's what makes Python nice. Along the course of executing that query, the intermediate result didn't touch the disk. It stayed in RAM. That's great. When we can do that, we're very happy. So, for MP3, which is coming tonight, all we're going to ask you to do, we've implemented a few algorithms for the different operators. And not very many of them. We just did the basics. We don't even have grouping. Like, it's just select, reject, and join. So the queries that we're going to be dealing with are very simple. And we implemented the cost estimation for you. The cost estimation equations that we're using are actually different than what you guys are going to use. The purpose of this is basically we're simulating what it would be like for you to try to optimize some query that, you don't know exactly how many tuples are in that table. You don't know exactly how many of them are going to join to some other table. So it's kind of a black box. So it's going to be your goal, your mission. We're going to give you 5 queries. And we're implementing them, in kind of a dumb way. And it's going to be your job to improve the query plan, to rewrite that in a smarter way. And you're going to have to keep within memory constraints, if we say that. So, you have a certain number of buffers to work with. You're reading in that, series of relations. Can you implement that query faster? Go ahead.
What language is it?
So it's exactly the same relational algebra that we gave you last time.
What language?
So it's in Python, but it's the same as it was before in that, like, you are only writing the you're not programming anything. You're just writing the query plan in the relational algebra. And when you stick your query plan in there, however you write it, like, we do all the estimation for you. So you should be able to just take, all the parameters for each one of the relations out to the disk, out to pencil and paper, write them down, and find the optimal query plan, and then just type it in. So it should not involve programming. It can involve programming if you want to be fancy. Right? You could actually try and write an optimizer for these things. If you're so inclined, that is cool. But you don't do it. So we'll release this tonight. We've spent a lot of time on it, so hopefully this is very clear, not as hard as the past one. Okay. So, we've reached a special point in this class. And as a result, I want to take a step back from the things we've been working on and sort of give you guys a sense of what you've accomplished now, what you actually understand. So, we started at the beginning of the semester. I put this diagram up on the board as like a joke. Right? I said, like, look at this whole thing, look how complicated it is. And everyone sort of laughed, like, yeah, I can't understand that. So far, we understand a significant amount of this. There's still some of it we don't understand. So, are you guys familiar with that? Old maps used to have areas, if people didn't know what was there, here'd be dragons, and it's dangerous over there. So, it's not mapped. So we don't know what's going on over there. But we do know what's going on this whole left-hand side. So I want to focus on that. That whole left-hand side tells you what happens when you type in a SQL query statement. Like, everything that happens between your query being entered as text and it going all the way down to the disk and computing your result. So because of that, I actually want to walk through that whole process. You guys should be able to understand, at least in principle, what happens all the way through. So, some user types in a query in SQL. So what's the first thing that happens to this query? What do we do first? Yes?
It goes through the query compiler.
Yes, so it's going to go to the query compiler. So that is indeed correct. So the query compiler has a series of things that it's going to need to do to that query. So what's the first thing the query compiler is going to do? Yes?
It's either convert SQL to relational logic or pretty parse tree.
So first it's the parse tree, right? The first thing we do is we actually use the SQL grammar and we're going to generate a parse tree. Yes, you are correct. So the first thing that we get is this parse tree that looks like we ran CYK across a context-free grammar, right? You guys aren't having PTSD from taking CS373, you know. Hopefully you remember that. Okay, what do we do with that? What happens next? So we tokenize this thing and parsed it. We have a parse tree. What happens next? What do we do with the parse tree? You actually made the right thing, didn't you?
Yeah. Convert MySQL into relational logic.
Yeah, so we're going to convert this thing into relational algebra. When we convert it into relational algebra, we call that our logical query plan. So, you know, basically we execute an algorithm over this tree and convert each one of the nodes along that tree into some kind of relational algebra. So now we have an initial query plan. What do we do with this initial logical query plan? So that thing was just sort of machine parsed straight from what the user gave us. And most of the time when people write queries in SQL, you guys have experienced this, I think, yourselves. You sort of just naively type in, hey, give me the answer. You don't worry about optimizing it yourself. So what happens
Yeah, I
now?
was just going to say it optimizes it.
Yes, yes. So the next thing we do is we try to find an optimal logical query plan, a better logical query plan. We can use heuristics to do that. For example, we should rewrite all of our cross products when we can as joins. We should push down selection and duplication. So for the sake of argument, let's say that we could do all of those things. So we push down our deduplication, we push down our select, and we've converted this cross product into a join, which really we can't do, but for the sake of argument, let's do that, because it's a little bit nicer to deal with. Okay, so now we have an optimized logical query plan. What do we do with that? I just told you that part. Yes?
They convert it into physical query.
Right, so we convert this thing into a physical query plan, which basically means that we go along each one of the nodes of this thing, and we're just flat out going to replace it with some choice. We're going to make some decision about the algorithm we're going to use to implement it. So we could, for example, say that we're going to access R. We notice here we have a selection. So in order to access that thing, maybe we should use maybe it's indexed on A. Okay, well if it's indexed on A, we should use that index to select those guys out. And then we should do this duplication elimination. How should we do that? Well, let's say we'll use the one-pass sort-based duplicate elimination. Maybe it's a small enough table that it fits in memory, so it's really easy for us to just, do the duplication all in memory. Okay, maybe S, though, is really big. So we can't fit all of S in memory. We can't even fit S in, a single table scan. We need to actually, in order to sort this thing, we need a two-pass sort. So in that case, we're going to choose to do the two-pass sort-based duplicate elimination on our table on A. So we'll just read in A, table scan A, sort it, in the process of sorting it, do the duplicate elimination, and because it's so big, we'll actually materialize that result out on the disk. And then, here, we're going to pipeline the result of our one-pass sort-based duplication into a final one-pass sort join. Okay? So we're taking advantage along the way that we're taking advantage of the fact that this is coming in sorted and this is coming in sorted. So that makes this joining easier. Okay. So now we have that actual physical query plan. What happens now is that query plan is going to get passed to the execution engine. The execution engine is, for each one of those operations it has to execute, it's going to request some buffers. Right? So the buffer manager is responsible over here for basically giving us some memory. Okay? And we're going to request for each one of those things, in order to implement them, we need a certain amount of buffers, right, just to get the work done. We're going to need a certain number of, or we're going to need access to the actual relations themselves, which are out on the disk, right? So we're going to have to ask this index file and record manager to go get those for us. And it will interact with the buffer manager to actually, bring those things in from the disk and put them in our buffers. So all along the way here, all this stage, after we actually have a physical query plan, this is all about getting the data to execute those things into the buffers, and then doing the algorithm, the operation that we just described on the data once it's in the buffers. And how does that stuff get into the buffers? Well, that's just a matter of the storage manager. It knows where everything is. It knows how everything's stored. It's going to just bring them all into memory. So let's see what that looks like. So, for example, let's start out, and we'll do this part of our query. So, accessing X. And we need to do a two-pass sort-based duplicate elimination on it. You guys remember how this works? So, the first pass, we read just as much as we can fit into memory, all those blocks, sort them in memory, write that out to the disk, bring in the rest of the blocks, sort those, write that out to the disk, and then for each one of the sorted sublists that we have, we're going to have one buffer. We're going to bring in each one of those sublists and merge sort those and write the results out to the disk. Here, we have a duplication. We have an instance of F appearing twice. So we'll do the duplicate elimination. We also have an instance of Q appearing twice. We do the duplicate elimination. And now we have that entire result materialized, right? We wrote the results all back out to the disk. So nothing was pipelined here. Okay? So we did our duplicate elimination. Let's do our index scanning. Let's choose all of the tuples of R that have attribute A greater than 3. Imagine that we have a B tree index. How would we find all the tuples in the B tree such that the attribute is greater than 3? You guys remember how to do this lookup? This is like a grand review. So how do I look that up in a B tree? Start at the root. I have 3 to look up, so is 3 greater than or less than 10? Less than 10. So I go to the left child of 10, and then I look in that block. I see that, well, there is an entry 3, so how do I find all the ones that are greater than 3? I follow all of the leaf pointers, right, to retrieve all of them. So I follow the pointers between the leaves So that would allow me to pull in all the tuples that have A, presumably, that second attribute is A, greater than 3. So I pull all those guys into memory. And now I'm going to do that a little bit of pipelining, right? They're already in memory here. I haven't written that result back out to the disk. I'm going to go ahead and sort that in memory because it all fits in memory. And, oh, yes?
So if you had to materialize the results from the 2-pass duplicate elimination, don't you have to materialize the result of the table scan too, since that would be bigger?
What's that?
So
Which thing am I materializing?
the 2-pass duplicate elimination.
Oh, okay. Let me go back. So you're saying, like here, should I materialize the result? No, because this is input. Right? Table scanning that is actually me accessing the entries of that thing one by one. If you want, that's actually doing the first pass.
Oh, okay.
The 2-pass. Okay. So now I'm going to pipeline what I just computed into my next 1-pass sort join. So I already have in memory everything from the first relation, R, sorted. I have materialized everything else from S, sorted. So now I just do, right, I need one buffer for a table scan and one buffer for output buffer whenever two things join together. So I can just read these blocks in one by one and look for things that join. So A joins with A here. And nothing joins here. Nothing joins here. T joins with T. And then finally, well, I could bring this last guy into memory, but we know that we're done, right? V is greater than everything that's in the other relation. We're done. So now we have our output. So we actually just walked from someone typing in SQL all the way to how it actually gets implemented in the system. You guys actually have learned something from all of this, believe it or not. This wasn't just useless, this wasn't just torture. You actually now know what really happens in a database management system when you type in a query and execute it. Again, it's a simplified view, but you took 233 maybe. Most of that was a simplified view. Right? Most of your understanding of Java is a simplified view. You have a model still, though, of how the system works, which is important. Okay, so let's go back to our big picture. Does anyone have any questions along the way for how this stuff works now? Our sort of grand perspective now. Sounds like we're doing okay, I hope. All right. So we have this big area that we don't understand still. So we need to fight back here a little bit against the dragons. So I don't know if you guys are Skyrim players. So let's actually fight back and try and understand this logging and recovery system. So the way that guy is drawn, do you guys notice what it's interacting with? Here, the logging and recovery system is interacting with the execution engine. And it looks like the execution engine is like giving data to our logging system. Essentially what this logging system is doing is it's keeping track of, right, we just talked about like what the execution engine does. It has all of those operators that it's doing, all those algorithms that we discussed, right? The relational operators. It's reading and writing a bunch of data in response to our queries. So, the logger is watching all of that happen. It's watching each one of our reads and writes. It's watching what transactions are happening in our database management system. Why is it doing that? Why should we care? Why don't we just let it happen? The problem is we could have system failures Or we could just have errors. So we want, if there's a system failure or an error, to be able to return the database to a valid state. So transactions that are completed should be durable. Transactions that are done should actually be written out to the disk. Right? So if the execution engine got done, actually finished, you typed, updates, personnel table, you typed a big query in there, and actually finished updating everybody's salary or whatever, you want that to live on the disk and persist forever. But if it didn't get done, if that transaction was still executing and then someone pulled the power on your server, you don't want half of the people to get a bonus and half of the people not to get a bonus because somebody pulled the power, right? So transactions that are not complete, those should be aborted. Those should be thrown away. So our logging and recovery system is going to be responsible for ensuring this. You guys remember we talked about the ACID requirements. And there was always this last thing, this notion of durability, and everybody kept asking, well, what about durability? What ensures that? That is the logging and recovery system. The logging and recovery system actually also is involved in some of the other ACID requirements, though. Can you guys imagine what those might be? I'll pause and see if you can suss that out. What was atomicity about? Yes?
The two activities should act as a whole, so it happens together. It doesn't happen manually.
Exactly. So our transactions either completely happen, right? The entire transaction executes, or it doesn't. Okay, what if somebody types half of a transaction and then they decide, I made a mistake, and then they type rollback? If they type rollback, what happens to that transaction? You guys remember what rollback did? We start a transaction, we start updating a bunch of stuff, and then we type rollback.
Doesn't it reset the database before the transaction?
Right, it resets the database to make it look as though that transaction never happened. Right? It erases it. It's aborted, right? We just get rid of it. So actually, our database management system's logging and recovery system is involved in ensuring atomicity. Also, if we had a transaction that was executing and somebody pulled the plug, again, if the transaction was only half executed, we don't, the transaction either completely happens or it doesn't. It can't half happen. So again, atomicity is actually partially ensured by our logging and recovery system. What about consistency? Do you guys remember what consistency was all about? It was kind of a weird one. So that was about constraints and triggers. Is this starting to ring a bell at all? No? No one remembers what consistency is about? Okay. Well, what is consistency about? Do you remember?
I mean, if you delete an entry from a table, you ensure that if there's a foreign key, then the other table it's also deleted.
Right. Right. So all of our constraints should be satisfied at all times. So again, if someone, if we're updating a table and someone pulls the plug, if our constraint isn't satisfied, right, we didn't check the constraint, but we still wrote a bunch of data, now our database is not consistent with our constraints. So that would also be bad. So our logging and recovery system actually is involved in most of these ACID requirements. It's a very important system. So I've been talking about transactions, right? The whole business about this logging and recovery system was in relation to transactions. So we need some way of modeling, in terms of the execution engine, what that is doing in terms of data. right? So we need a way of modeling transactions and how transactions manipulate data. So we have a few things that we're going to call primitives of transactions. And this is a little bit abstract. So we can say that we input some database element X into a memory buffer. This database element X, what we mean by database element, is left deliberately a little bit vague. So we could mean a tuple. We could mean a relation. Usually what we're trying to get at is one block of one relation. So that is the notion of inputting a thing. We can also read a database element. So we can read some database element off the disk and assign it to a specific variable. This is a memory variable. This is what you're used to coding in like C. So we brought the thing into memory, we've assigned it to some temporary variable in memory, and then we can potentially modify that temporary variable. After we change that temporary variable, we can write it back into that block. We can write it back into the database element. So that's now, in memory at least, we have a record that, has been altered, or we have a table that's been altered. But it hasn't been written to the disk. It's still in memory. So until we say output X, we don't write any results back to the disk. These primitives should be similar to things that maybe you've encountered in, so you would encounter these in architecture if you were dealing with like cache coherence. You might see primitives like this in networking. So it's the same kind of notion. We're dealing with modeling at some level of granularity the operations of these transactions. And we're going to come up with rules for like manipulating. Yes?
So this is just pseudocode, right?
Yeah, in a sense you can think of it as pseudocode. Yeah. Okay. So let's go through an example. This should make it a little bit more concrete. So let's say there was some constraint in our database that A equals to B. What specifically is A or what specifically is B? It could be anything that's in the database. So you could think of this as being, for example, two specific tuples that always have to, agree on some value. So, for example, a foreign key, right? Maybe we're talking about a foreign key. So we have some transaction, and that transaction is going to set A equal to A times 2, and it's going to set B equal to B times 2. So our constraint should be satisfied, right? After we're done executing this whole transaction. How would that actually get executed? How would that actually happen? So the first thing that we would need to do is read A. We would need to read A into memory and then assign that to some specific temporary variable T. Okay? If you look out on the disk, we still have that A and B are both 8. So those are like their initial values, and that's their value out on the disk. When we bring A into memory, the memory value for A is 8. And then when we assign it to this temporary variable T, the value of T is 8. Okay, nothing interesting has happened yet. We multiply T by 2. So now we have T is 16, but A has remained the same. So until we write it back into A hasn't been modified. So write T into A. Notice that A remains the same on the disk though. Now let's read in B and assign that to T. We'll multiply that by 2 and write that result back. So now in memory we have both modified values of A and B. They've both been updated in memory, but neither one has been updated on the disk. You guys remember what thing updates them on the disk? Which one of our primitives? Output, right? So the next thing we should do is output A. So now A has been modified on the disk. Output B. Now B has been modified on the disk. Yes?
So we're doing machine code right now.
It's kind of like machine code. It is a little bit like machine code, but it's again abstracted. What we would actually be programming for, these primitives are all things that the execution engine would actually deal with. So the execution engine would deal with all of these things. Right? So while it was going along and executing our operations, presumably it will be represented in terms of, at least we're modeling it in terms of these primitives. Okay, so we're going to look at one model of doing this logging and recovery system. So we're going to just do one. And then we'll continue this next time. So we're just going to look at the notion of undo logging. So this should be kind of familiar to you. So this is exactly like it sounds, right? If you type a bunch of stuff into your text editor and then you type undo, it undoes those things, right? So the main idea of this is that we're going to keep track of all of the values that we change. So every time we modify some value, we're going to remember what the old value was so that we can undo it if we need to. And then when we recover, right, so when the system fails, we can restore the old values for all the incomplete transactions. So if a transaction isn't done, we want to abort that transaction, what we can do is just go through our log, find the old value, and restore the old value. So in addition to those primitives, right, we needed some representation for how essentially the execution engine was dealing with data. We also need some way of representing what we're logging. Okay? So we're just going to think of the log as one long file that we just append things to the end of as we go along. And we're going to describe each of the entries like this. So start T would mean that transaction T has been started. We've written that into the database. We've started executing that transaction. We write that to the log. Commit T. Commit T means that we're done with that transaction. That transaction is complete. Everything, all the work that it was doing has been successfully finished. Abort T means that this transaction was unsuccessful. And then finally, we have this, which is the most interesting type of entry, which is, this is saying that some transaction T has modified the database element X, and the old value was V. So this is how we remember what the old value was. So for undo logging, what we're going to do is every time, we're going to watch the execution engine do its work, okay? And every time before it writes a new value to the disk, before it modifies some database element, we're going to, in our log, write what the old value was. And then, after all of the results for a specific transaction have been finished, it's completely done, then we will write commit. So we have to make sure all the results have been written to the disk first. So, for example, here's that transaction that we just witnessed. Right? I took you through that entire transaction executed. So before this transaction even starts, we should log that it has started. So someone has started some new transaction, we'll call it T. They read in A, just like we described before. They modify the temporary variable T. We don't even care about that until they write that T back into A. Now they've modified the value of A. Now it's our job, before they write that back out to the disk, we have to log what the old value was. So that's what we've done here. Remember the old value. Okay, this same exact process gets repeated for for B. Right? Someone reads in the value, we don't care about that. They modify the temporary variable, again, we don't care about that. But then when they write the result back into B, you have to remember the old value. So here, you remember that the old value was 8. Now, what is this? We did not see this before. Flush log. Okay. The log itself, we're writing to. It is a buffer in memory. Everything that you write from some program lives in memory. In order for it to be durable, it has to live on the disk, right? So our execution engine, before it commits, before it outputs these values to the disk, what it's going to do is flush the log. It's going to take all this work that we did so far, all these entries that we have, and actually write those out to the disk. So that's what this flush log business is all about. Then we will commit the values that we just updated out to the disk. Now that all of this has been successfully executed, this transaction is complete. So we can commit that transaction. And then we should probably flush that result back out too. So then our log file has a record of just this over here. So that's what our log file looks like. It's on the right. On the left, we had all of the transaction executed in the execution. So are there any questions on how this works? How we, sort of snoop what's happening in the execution engine, and based on that, write things out to the log? Yes?
So the logs disappear after you commit, right?
I'm sorry?
The log disappear after you commit that.
No. So right now, this log file always just gets bigger. Okay? So the flush flushes it out of memory and onto the disk. Right? Usually when you're writing some values into memory, those are just in memory, and that's temporary. So we have to flush that out to the disk. Then it's permanent. But for now, then you've actually noticed the problem, which is that this system, we never erase anything in this log. Our log file is just always going to get bigger. So as people continue executing transactions, this log file will just perpetually grow bigger and bigger and bigger. Eventually we'll deal with that. We'll talk about that on Friday. Okay, so here is the algorithm for recovery. And this is actually beautifully simple. So all we do is, we know basically that if we see a start transaction without a corresponding commit, then we have to undo that transaction. Right? If the system failed before that transaction was committed, then that transaction failed. We need to get rid of it. So how do we do that? All we need to do is start at the bottom of our log and work backwards. So start at the last thing we see. If we see a commit of some transaction F, right, we know that that transaction was finished. Right? So we can ignore that transaction. So we start at the bottom. Every time we see a commit, we remember, oh, that transaction completed, so it's fine. I will ignore it. I will let it live on the disk and keep all its values. But any other transaction that I'm not ignoring, right, it didn't have a commit. So that means that work needs to be undone. So I just go back and write the value that I remembered into X each time I encounter a record that's like this. So what would that look like? Here we have an example. So we start at the end of our log. Have I seen transaction T4 commit? No, I just started. So T4 didn't commit. So that means I need to undo this transaction. So that means I need to write a 3 into the database element X. Okay. I successfully undid that. It's as though that never happened. Commit T3. Okay. Now I need to know if I see anything from transaction T3, that should stay on the disk. I should not undo it. Okay. Start T4, I don't care about that at all. Nothing from my recovery algorithm talks even about what to do on starts. Ignore it. T3. Has T3 committed? Yes, I just said that, right? So I should ignore this. I should leave it. That was modified and that's okay because that transaction committed. Same for this. This entry in the log is also okay. That transaction was committed. Transaction T1. Have I seen it commit yet? Nope. So that means I need to undo this. That means I need to write a 1 into the database element D. And start T3, who cares about that? T2 committed. So T2, if I see anything from T2, it should stay on the disk. It should persist. I don't need to abort that transaction. So here I have an entry for T2. I should leave that alone. What about this one? I should undo it? Yes, I should undo it because I haven't seen T1 commit. Okay, start T2, T1. I should also delete that, right? Undo that, and undo that. Go ahead.
So when you undo T1A5, aren't you also inadvertently undoing T3A3 because you're overwriting what's in A?
Yes, potentially. So that's an issue of concurrency. So that is actually a really good question. So we actually have seen an issue here, which is we just overwrote A. Whatever database element A is, in the process of doing our recovery, we overwrote it with a 5. Over here, transaction T3 committed, and we just undid its change. The problem here has to do with concurrency. These two transactions were modifying the same value. We haven't talked about concurrency control yet. So that is an awesome question. There are actually entire systems, in the database concerned with managing that. We haven't gotten there yet. We just have to trust that the concurrency control system did the right thing, and that our undo logging is undoing the right thing too. Very good question. Yes. Anything else?
When we're logging, how do we ensure there's atomicity between when you put in the log and when it happens on the disk? Because you don't want.
Right. So the concern is atomicity between essentially so that's why we had this flush here. Right? So that ensures that whatever was in the log gets written out, we wait for that to finish, then we do these out operations. So each one of these is happening in the execution engine. So it's keeping track of it. Good. So I hope you all feel better than you did week on Friday. Okay. If you have any questions, feel free to ask. The MP will be out tonight. What's that? Oh, I think I'm going to give you a week from Friday.
When you say you're stuck, files and then it's also yeah. Just like a third of like if you want to set up right now.
You know, if you have like an that seemed like
right, what you tossed me minus something in.
So yeah. And on that, but again, solidly written with some
individual paper or
that, yeah.
So and then just like some calculated thing.
Yes, but then again, I definitely want that.
Okay, so maybe like emailing the TAs, like, you know, here's a copy of information, here's some of the
yeah, just email them. That way, it seems like
yeah, I assume just don't like, I assume that separate contracts for what you're planning, but he doesn't
involve in anything, but he's the one who does all the project.
Oh, he does not actually projects.
And he doesn't want to, yeah, the other thing I think he doesn't want to do is miss, like, really high standard when he's expecting the grad students. I don't know this, but it's just like,
yeah.
So, I'm okay. He wants to set that bar really high and make it like,
no, I guess
research for the really you're showing
so it's quite
working towards something related to research.
You decide you want to later.
And would you say or just like general research? When you say you want some more like I don't really know more about like general research. Like things without like telling them or more about review or
Especially
yeah.
What do you have to do today?
That's what they consider.
Oh, 410, yeah, okay, that's perfect. So, if you're interested in documents, how to measure them, you could go and find thousands really take your time. If you know a way that you and have your own experience and welcome to like
It's easier.
don't feel like you can't.
Okay. Yeah, but if if we're doing
the thing I'm trying to say is like
you want to use it.
okay, don't feel like it's just read this paper and then rotate what they're doing. Feel like really feel free to say like this is a dumb idea. Even but I mean, if you want to criticize or if you want to
Is the front end you just
if the paper's inspired, okay, maybe you could try this technique in this domain or anything like that. That would be really interesting. Yeah, but it would also be more important to get rid of it.
And I got the user because that's the table where.
So does that give you an idea of what you're
Yeah, so then you like you said like at least 15 pages or so, if we count it 55 years, like blood grade plus one.
Yes.
Yeah, that's why I'm always worried about like that. Like there's not like a and stuff that's like not being able to get any or any lines.
That's you do know. I would say meaning like plus minus. So don't kill yourself. Trying to get across that. We're going to have games that usually what I'll do is look at the final distribution and it's so it's not like a
Yeah, I mean, I don't like
dividing line arbitrarily based on some statistics. I'm going to actually web service here.
Well, we're making millions of dollars a year.
trying to say, don't worry about like optimizing that equation.
Right. I'm sure you mean everyone else. So you know, like the old like 90 degree scale being like 80, 90, whatever, right? And like those people, it's what this one is showing. Like it was always 20% of
right, which is fine. Like it's giving you, a big condition for. I'm just trying to say. How's your project going?
It's going good. I mean, we reached a whole little thing. It took us forever to get data files. We were looking at like engineering IT to quote out how many files we have in the server. So I emailed it back and forth several times and it increased enough that like particular we install properly. So luckily we all have our own little parts going on, and we're just hoping by the end of this week to have all the basic functionality done, spend all the next week implementing advanced functions, and then last week to just get it's also UI design project, so we've got to look good. So we'll see how it goes, and we'll hopefully eventually turn into something, because we have all these moving packages so we don't get busy. Like I have 391, so I have all this operating system stuff that I can live on me, and that's god awful. That's crunching up just one semester. But yeah, at least like we're all looking on parts, we just gotta like get going at it. Just probably spend like a couple nights straight just working on it. And actually, I think the advanced functions, I'm just trying to find like for sure we want to. Because I mentioned before, like 2 or 3 ideas that we had, and we're still like remember what I was